Hello and welcome back. This is video 15 of Humans versus AI. And in this video, we're going to use the model that we trained in the last video to play the game. We've got most of what we need already, so this will be nice and quick to get to a nice result where we'll see the AI actually playing the game, which is quite exciting. I have a Patreon account, so please do check it out if you'd like access to the code and like to support the channel. Thank you very much. Okay, moving on. Right. Let's go over to tensorboard. In the last video, we introduced this, which is tensorboard, a fantastically useful tool for viewing the performance of the model whilst it trains. I drew your attention to two of the default metrics that come out of the PPO class that we use, which tensorboard reads in. That is the average episode length that comes out of each rollout, and the average reward that comes out of each rollout. So both are very useful. The reward, of course, is the average reward that the machine has collected during the episode on average. That means that it's done well because it's got the highest reward. And to see it plateau like this suggests that the model has reached a solution which it considers is pretty optimal. It's unable to find any better solutions. So this should be quite optimized. And then the episode length, of course, we want it to be as short as possible because the objective is for the player to collect the energy as quickly as possible, and therefore the shorter the episode length, the better. Here we've got three lines, trend lines, showing the performance of the model on these two graphs. So we've run it 3 times. Before this video, I ran pink one, which is the latest model. So if I shut down the other two from the last video, we'll see that the pink training run resulted in something converging around 40,000. So in the training run I did earlier, I terminated the training at 40,000. So I set the number of steps to 40,000 because I knew from previous runs, which went on for much longer, as you can see, up to 100,000, I knew that they basically plateaued, and 40,000 was a good place to pick and save the model at. Now, in the next few videos, we're going to solve the problem of having to look ahead and then go back and stop the model at an appropriate point, because this won't actually always work. Reinforcement learning models can be quite unstable. So we're going to have to save the best model as we go, and we'll look at that in a later video. But in this video, we want to use the model, the one that I saved when it got to 40,000, in our game. So let's go back over to the code and start doing that. So if you remember, when we're training the model, at the end of the training process, we get something called, well, in this case, energy collection model.zip, which is a zip file containing the model, which is a series of weights. This comes out of, if we go into the PPO class that we've been developing in the last few videos, and we go to the bottom, we've got the train model method, which is what we're calling, if I go back to main, if we go down to the entry point of the whole application, you'll see that train model is a method that we're calling. That's where the training is happening, if train mode is true. Now going back to that then, it's in train model, which is where we have the save method, which saves the model, and it saves it here as energy collection model. So hopefully that's all clear and makes sense. Now, what we're missing is we're not using it. If we want to play the game, we need to use it. Against the AI at least, we need to use it. So the first thing we're going to do then, in order to use it, we're going back to main, where we're going to be using the model to play the game. The first thing is I have imported the PPO, the PPO class from Stable Baselines 3. This wasn't here before. We imported it into PPO.py before because we needed it. There it is. But we didn't include it in main until now. But of course we need it in main because we're going to use it to load the model. Right, let's scroll down. Now, in order for the machine to play the game, we need to load the model during the setup phase. If you remember, setup is a method that I created way early on in this series, which is the precursor to the game starting. It does the setup process, does the checks for sanity checking the settings, builds the texture for the grid, sets up the players on the grid, sets up the energy on the grid, resets some state, which we need to do both for training but also in case the player has another go during the same instance of the program running. But now is the new bit here. So what we say is, if we're not in train mode because we're going to play the game, then read in the model, self.model, which is defined as none. Oh, it should be defined as none. It isn't, but I'll sort that out later. So self.model should be none. I'll just put that in there. It'll work anyway, but we'll do that for completeness. There we go. What we're saying is, if we're not training, define the model as this, which is loading the model using the PPO load method from the model path, which points to energy collection model.zip in constants. If we go to constants just to show that, we've got here model path. And it says to use the CPU as the device to run it on, which again, as I've mentioned before, for a multi-layer perceptron artificial neural network type policy in PPO, the CPU is actually better. So this means when setup is run, when we're playing the game, the model is loaded into self.model. Now we need to use it, of course. So if you remember, we've got two loops that Arcade runs consistently. The draw loop, which is for rendering what's on screen, and onUpdate, which actually runs just before the draw loop. And within onUpdate, it's in here where we're controlling the players. We have the player being controlled by the keyboard, and what that does is it sets the target position for the player based on the keyboard stroke. Or if it's the machine learning player, we are going to be using the output from the model. And this is where I've commented in this line, which in the last video I commented out. And this, I haven't really explained this yet. So this is the way in which you run an already trained model at inference time. So you want to get an inference from the model. It needs to infer something. So you use the predict method associated with the model that we've created from the PPO class. So this is our model. We're using the predict method that comes with it, and we're going to pass it in its observation, which is in this case called state. But this is the state of the game, and it's also it's the selected state. If you recall, it comes from these methods that we've covered in the previous videos. It's the observation of the machine learning model. So it takes the observation as an input, and out of it comes action, which is what we need. That's a number between 0 and 3, which defines which way the machine has decided it wants to go based on the input state, its observation. Right, so with that explained then, we can now, instead of having a placeholder, what we had before, which was action equals 3, we can actually use the action from the model. And this is therefore going to work properly. We're going to set the target position using the ML set target position method that we created in a previous video, which simply sets the target coordinates for the player, whoever you're passing through. In this case, it's the player within the player loop here. So it's one of the players, and we're going to use the action that the machine suggested. So just to confirm, let's go and have a quick look at what that method looks like. So again, as you can see, it takes player as an input, and ultimately what it's doing is it's setting the target X and target Y positions here using the set target positions method. The rest of this is here just to prevent the player going beyond the bounds of the game grid, if you recall from an earlier video. So there we go. That will have set the target position. So the next thing then to do is to go to constants and check we're going to play the game now. So I'm going to set player to true so that I can play it. Actually, I'll set player to false first, and I will set the number of players to 1. And I will set train to false, which is what it should be, which means this should play the game. So let's see what happens. Theoretically, let's see. Fingers crossed, because I haven't tried this before the video. We should see the player play the game. Ah, there we go. Is it nice? Yep. Okay, wonderful. The player had to collect 3 energy points to win. It got the first energy point immediately, then it collected the other 2, and it has won. And that was done by the AI. And I should be able to click a key. There we go. Let's just do it one more time to check it wasn't a fluke. Not that I expect it was a fluke. There we go. So what's happening is with every iteration of onUpdate, we are getting an action from the model based on the input state. And if you remember, the input state in the model is the relative positions of the energy compared to the player and the absolute distances of those energy points to the player. So that's all the game machine learning model, needed to know of the game in order to learn those relationships. Now let's make it a little bit more interesting. Let's make it so that I can play as well. Human player true, energy to win 3, players 2. Okay, let's see. Press play. So I'm going to play now with the keyboard. I need to get ready. I'm almost certainly not going to win this. In fact, the player's already beaten me. Oh, nobody wins. It's a draw. So you get the idea. So we've got to the stage now in video 15 of actually being able to play against an AI, which is quite good fun. He's going to get 2 and I'm going to get 2. It's going to be a draw again. So largely the game is more about where you start compared to the energy, of course, but we are going to make it more interesting as we go. But this is a good place to start. Now, for the sake of completeness, because AI can play against itself, I'm going to set myself as false. I'm going to say there's going to be, let's be silly, 4 AI players, and they have to collect 2 energy to win. I can't change the number of energy points, which is an interesting point to draw attention to. The energy points define the input vector, if you recall, and the model requires that to stay the same size, if you recall. So I can't change that without changing the model, and we have to solve that later on. So if I run it now, I'm not playing this anymore. It should just be 4 AI players. There we go. I doubt anyone's going to win because they've got to collect 2. Ah, player 2 did win. There we go. Ha. Okay, now we could consider this job well done. We could say, well, we've got to where we wanted to be. But actually, I've got here because I know it's going to work, because I've gone through the process and the journey. And there are tools that you don't yet have if you're following this course that will make this process of getting here much easier. So in the next couple of videos, we're going to explore those tools, how to visualize what's happening, how to optimize the model and tune the pre-parameters. So there's still some way to go to do this in a better way. And we're going to make this more difficult for ourselves, because the current game, which has just a 10 by 10 grid, is relatively easier to train on. It gets much harder as the grid gets bigger. And you can imagine why that would be, because as the grid gets a lot bigger, it's not just that there's more to learn. Yes, that's true. It's harder for the machine to learn the patterns, but that's not really the big issue. The issue actually is that if the grid is much, much bigger, it takes longer to complete, particularly the first few episodes, because in order to complete an episode, the player has to collect all of the energy. And if the grid's much bigger, and at the start of the training process, if you remember, the player moves around very randomly as it explores the environment. It can take a very, very long time for it to start to learn the patterns. And so the learning, the training, can go from converging in 40,000 to converging in 400,000 or more. So we'll look at that as it gets more complex as we go. So I look forward to seeing you in video 16 as we begin visualizing what's happening in more detail, looking at the reward landscape in space across the grid, but also in time to see what the reward looks like as the machine goes. Because as we make changes and increase the complexity of this game, we're going to need to visualize the rewards and potentially change them as well. Okay, thanks again, and I will see you in the next video.